lesson 2, graduation of the properties of elements in the modern periodic table. This lesson is talking about the position of elements in the modern periodic table according to their properties. The three properties in this lesson are atomic size, electronegativity, metallic and non-metallic properties. So we have three properties in this lesson, which are atomic size, electronegativity, metallic and non-metallic. And first we will talk about these properties in group A. First, atomic size. Atomic radius. What is the atomic radius? The atom looks like a circle or a ball. So the radius of the atom is the same like or looks like the radius of a circle or the radius of a ball. If you want to measure the size of the atom, we must measure its radius, the atomic radius. And because the atom is very small, we can't see the atom. So its radius is not measured by a meter, it's measured by a very small measuring unit called picometer or PM. Graduation of atomic size of elements in the periodic table. First, we'll talk about the atomic size in periods. In periods, by increasing the atomic number from the left side to the right side in the period, the atomic size will decrease. So the atomic size decreases as we go from the left side to the right side in the period. Why? Because the attraction force between the nucleus and electrons increases. Nucleus has a positive charge and electrons has negative charge. So the attraction force between the positive nucleus and negative electrons increases and electrons get near to the nucleus. That's why the size will decrease as we go from the left side to the right side. So again, in the period, the atomic size as we go from the left side to the right side by increasing the atomic number from the left to the right, the atomic size will decrease. Atomic size decrease by increasing the atomic number. So there is indirect relation between the atomic size and the atomic number, because by increasing the atomic number, atomic size decreases. So that's indirect relation. So the atomic size inversely proportional to the atomic number. And this graph shows the relation or the indirect relation between the atomic size and the atomic number. So here in the modern periodic table, if you look at period 2, which has lithium and beryllium, we can see that beryllium has larger atomic number than lithium, because as we go from the left side to the right side, we know that the atomic number increasing but the atomic size decreasing. So beryllium will have smaller atomic size than lithium. And also in period 3, which is having sodium and magnesium, magnesium will have smaller atomic size than sodium, but it has larger atomic number, the atomic number increasing but the atomic size decreasing. Okay, in period 4, for example, calcium will have smaller atomic size than potassium. In groups, by increasing the atomic number from up to down in the vertical column, the atomic size increases. Why? Give reason. Because by increasing the atomic number, we need more energy levels to distribute the electrons, those electrons. So by increasing the atomic number from up to down in the group, we need more energy levels, so the number of energy levels also increases. So by increasing the number of energy levels, the size of the atom will be larger. So in the groups, by increasing the atomic number from up to down, the atomic size increases. Why? Because the number of energy levels increases, and this gives the atom more size. As we have more energy levels, the size of the atom will increase. So here we give reason. Due to the increase in the number of energy levels. So the atomic size of elements of the same group is directly proportional to the atomic number. Here we have a direct relation between the atomic size and the atomic number in group. In period it was indirect relation, but here in group it's a direct relation between the atomic size and the atomic number. If we make a comparison between lithium and cesium in group 1A, lithium is in period 2, cesium in period 6. Okay, lithium has less atomic number, but cesium has a larger atomic number. So the number of energy levels in lithium will be less than the number of energy levels in cesium. Lithium has only 2 energy levels, but cesium has about 6 energy levels. So as we can see here, the atomic size of cesium is larger than the atomic size of lithium. Why? Because the number of energy levels in cesium is more than the number of energy levels in lithium. Lithium is in period 2, up in the group, but cesium in period 6, down in the group. So as we go from up to down, the number of energy levels increases and the atomic size increases. Conclusion: in the period when the atomic number is increasing, attraction force increasing, atomic size decreasing. Atomic number increase, attraction force increase, atomic size decrease. Increase, decrease. And that's indirect relation between the atomic number and the atomic size. But in the group, when the atomic number is increasing, the number of energy levels is increasing, so the atomic size is also increasing. So atomic size increase, energy levels increase, atomic size increase. And here we have direct relation between atomic number and atomic size. So in period, increase, decrease. In group, increase. In period, indirect relation between atomic number and atomic size. In group, direct relation between atomic number and atomic size. Here, if we look at periods, we can see that the atomic radius or the atomic size is decreasing as we go from the left side to the right side. So the atomic size is decreasing from left to right. But in groups, the atomic size is increasing as we go from up to down. In the same group, the atomic radius and the atomic size is increasing in groups, but in periods, atomic size is decreasing. Here we have another conclusion. In periods, the atomic size decreasing as we go from the left side to the right side. Why? Because the attraction force increases. So atomic size decrease, attraction force increase. So if we look at the element in the first period on the left side, we can see that it has a larger number than the element on the right. A larger atomic size than the element on the left side. So again, the element on the left side in periods has larger atomic size than the element on the right side in periods. As we go from left to right, we can see that the size is decreasing, atomic size is decreasing. Why? Because attraction force increases. But if you look at groups, we can see that if we go from up to down in the group, the atomic size is increasing. Atomic size is increasing from up to down, as in the first group here and in the last group here. The element up in the group has smaller atomic size than the element which is down in the group. From up to down, size increasing. Why? Because the number of energy levels increases. So in group, the atomic size increases. Why? Because the number of energy levels increases. So in period, atomic size decrease, attraction force increase. In group, atomic size increase, the number of energy levels increase. First, atomic size. Atomic radius. What is the atomic radius? The atom looks like a circle or a ball. So the radius of the atom is the same like or looks like the radius of a circle or the radius of a ball. We said in this lesson we will talk about three properties which are atomic size, electronegativity, and metallic and non-metallic property. We finished atomic size. Now we will talk about electronegativity. What is electronegativity? Electronegativity is the ability of atom to attract the electrons in covalent bond. We studied the covalent bond in middle one, and a covalent bond it's a bond between two elements, and each element has to share the same number of electrons between each other. Okay. If any element can attract the electrons towards itself more than the other element, we say this element has larger or higher electronegativity. So electronegativity is what? Is the ability to attract the electrons, the ability of element to attract electrons towards itself. If the element can attract the electrons towards itself in the covalent bond, we say it has electronegativity. So again, what is electronegativity? Electronegativity is the ability of atom in covalent bond or covalent molecule to attract electrons towards itself. The more the electron can attract the more the element can attract electrons, the more we say it has electronegativity. The more electronegativity it has. So electronegativity is related to what? Is related to attraction of electrons. Electronegativity is related to the attraction of electrons. Now we will talk about the derivation of electronegativity in the modern periodic table. First, we'll talk about it in periods. In periods, by increasing the atomic number from the left side to the right side, electronegativity increases. So, by increasing the atomic number in periods, electronegativity increases. Why? Because we said before, when we talked about the atomic size, that the atomic size decreases in periods because the attraction force increases. So in periods, attraction force increases from left to right because the attraction force is increasing, attraction is increasing, so also electronegativity will be increasing because we said electronegativity is the ability to attract, electronegativity related to attraction. When the attraction increases, electronegativity increases. And we said in period, attraction force increases. So also electronegativity increases in periods. And as we said, the atomic number is always increasing in periods and in groups. So by increasing the atomic number, electronegativity increases in periods. And it's a direct relation between electronegativity and the atomic number. Okay, electronegativity in groups. Now we'll talk about the electronegativity in the group. We said that the atomic number is always increasing. So by increasing the atomic number in group from up to down, electronegativity decreases, and it's indirect relation. So in group, electronegativity decreases by increasing the atomic number. Why? Because we said in group, from up to down, the number of energy levels is increasing. So the electrons go away from the nucleus, go away from the attraction. As the electrons are far away from the nucleus, so the nucleus can't attract them. As the electrons are far away from the nucleus, so the attraction decreases. The nucleus can't attract them. Okay, so the attraction is decreasing. That's why electronegativity will be decreasing, because we said electronegativity is related to the attraction. So again, in groups, we said that the number of energy levels increases, and as the number of energy levels increases, electrons are far away. The distance between the electrons and the nucleus is increasing. Electrons are far from the nucleus, so the nucleus can't attract them, so the attraction is decreasing. That's why electronegativity is also decreasing. So in groups, by increasing the atomic number, we said atomic number is always increasing in period and in group. So by increasing the atomic number, electronegativity decreases, and it's inversely proportional or in direct relation between electronegativity and the atomic number. We have an example between lithium and cesium. Lithium and cesium, both of them are in group 1A. Lithium is up in the group but cesium is down in the group. Okay, lithium has just 2 energy levels, but cesium, because it's down in the group, and we said as we go down in the group, the number of energy levels increases. Okay, the electrons here in lithium, in the second energy level, the distance between that electron and the nucleus is small, so the nucleus can attract it. The attraction here is large, so electronegativity in lithium is large. But in cesium, the last or the outermost energy level, the distance between the electron and the outermost energy level in cesium and the nucleus, the distance between the electron and the nucleus in cesium is more than the distance between the electron in the outermost energy level and the nucleus in lithium. The distance in cesium more than the distance in lithium. So the attraction in cesium will be smaller than or less than the attraction in lithium. So attraction in cesium is less than attraction in lithium. Why? Because the number of energy levels in cesium is more than the number of energy levels in lithium. So the electrons, the distance between the electrons in outermost energy level and the nucleus is more than the distance in lithium. As the distance increases, the nucleus can't attract, or the attraction is decreasing between nucleus and the electrons, and as the attraction is decreasing, that's why electronegativity also decreasing. So in the group from up to down, the attraction decreases because energy levels increases, and the nucleus can't attract the electrons well as the energy level is increasing, so electronegativity is decreasing. So again, attraction decreases, so electronegativity decreases. Attraction decreases, electronegativity decreases. That's in the group. Picture here showing the relation between electronegativity and the atomic size in periods and in groups. Here in periods, we said from the left to the right side, electronegativity is increasing, but atomic size is decreasing. But in group, from up to down, electronegativity is decreasing, but the atomic size is increasing. So, in period, electronegativity increases, atomic size decreases. In group, electronegativity decreases, atomic size increases. So the relation between atomic size and electronegativity is indirect relation or inverse relation. Fluorine has the highest electronegativity. Why? Because fluorine has the smallest atomic size. We said there is indirect relation between electronegativity and atomic size. So, because fluorine has the smallest atomic size, that's why it has the highest electronegativity. Note number 2, the inert gases haven't electronegativity. The inert gases have no electronegativity. Why? Because the inert gases don't enter in the chemical reactions. They don't share electrons. So they don't have electronegativity. So again, inert gases have no electronegativity. Why? Because they don't share in chemical reactions. Note number 3, the difference in electronegativity determines the kind of ionic bond. Again, the difference in electronegativity determines the kind of bond, if it's ionic or covalent bond. And we'll know how in the next slide. We said that the difference in electronegativity between the two elements determines the type of bond. If the difference between the two elements in electronegativity is less than 1.7, so the bond will be covalent bond. But if the difference in electronegativity between the two elements is more than 1.7, so it's ionic bond. So again, less than 1.7, covalent bond. More than 1.7, ionic bond. The covalent bond has two types of compounds. The compound may be nonpolar compounds or polar compounds. In the nonpolar compounds, the difference in electronegativity between the elements is a small value, like methane, hydrogen sulfide. So, if the difference in electronegativity is a small value, less than 1.7 and it's a small value, so it's a non-polar compound like methane and hydrogen sulfide. But in polar compounds, the difference in electronegativity is relatively high. Okay, it's not more than 1.7, but it's still high. Like what? Like water and ammonia. As we said, the non-polar covalent compounds has a small value of electronegativity. Like A and B, the difference between them is very small, so they are non-polar. But the polar covalent compound here between A and B, we can see that B has larger value than A, so the difference between them is relatively high. So the polar covalent, the difference is relatively high. But in the ionic, it's very high. So that's why we said in the ionic bond, the difference in electronegativity is more than 1.7, but covalent less than 1.7. And as we said, covalent has two types, polar and non-polar. The difference of electronegativity in non-polar is small, but in polar is relatively high. So there is difference between A and B. B is larger. That's why the difference is relatively high. But in the ionic, because it's more than 1.7, so it's higher. It's higher than the polar covalent. Here we have a comparison between polar compounds and non-polar compounds. We said in polar compounds that the electronegativity is relatively high. So the polar compound is a covalent compound and the electronegativity between its elements is relatively high. But in non-polar compounds, the difference in electronegativity is relatively low. Okay, and both of them are less than 1.7 because it's a covalent bond. Okay, we said that the covalent bond, the difference in electronegativity is less than 1.7, but in polar is relatively high, and it's almost 1.7 or less by a little amount. But in non-polar, the electronegativity, the difference in electronegativity will be relatively low, much less than 1.7. Okay, in polar compounds, the examples we have water molecules and ammonia molecule. First, water molecule. The water molecule consists of two hydrogen atoms and one oxygen atom, H2O. So it has one oxygen and two hydrogen. The electronegativity of oxygen is 3.5 and the electronegativity of hydrogen is 2.1. If we calculate the difference between the electronegativity of oxygen and the hydrogen, 3.5 minus 2.1, it will be 1.4. It's still less than 1.7. Okay, but it's near to 1.7. So it's relatively high. So it's a polar compound. For ammonia molecule consists of one nitrogen atom and three hydrogen atoms, NH3. One nitrogen, three hydrogen. The electronegativity of nitrogen is 3 and the electronegativity of hydrogen is 2.1. If we calculate the difference between them, 3 minus 2.1, it will be 0.09. It's also considered relatively high if we compare it with 1.7. Okay? But for the non-polar compounds, we have two examples, which is methane. Methane gas consists of CH4, one carbon atom and four hydrogen atoms. Carbon, its electronegativity is 2.5. Hydrogen, its electronegativity is 2.1. If we calculate the difference, 2.5 minus 2.1, it will be 0.04. And it's considered relatively low if we compare it to what? To 1.7. Because polar and non-polar, both of them must be less than 1.7 because they are covalent bonds. So here methane gas is 0.04, so it's much less than 1.7, so it's considered relatively low. That's why it's a non-polar compound. Okay, for hydrogen sulfide, H2S, it consists of one sulfur one sulfur atom and two hydrogen atoms. The electronegativity of sulfur is 2.5, but the electronegativity of hydrogen is 2.1. If we calculate the difference, 2.5 minus 2.1, it will be equal 0.4, and it's also relatively low if we compare it to 1.7. You don't have to remember those numbers just to understand them. So again, the comparison between polar and non-polar. Polar, the difference in electronegativity relatively low. Polar relatively high. In polar, relatively high. Non-polar, relatively low. Examples for polar: water molecule, ammonia molecule. Examples for non-polar: methane gas, hydrogen sulfide. Give reasons. Number 1, water and ammonia are from polar covalent compounds. Why water and ammonia considered as polar compounds? Because the difference in electronegativity are or is relatively high. Okay, if he's asking about hydrogen sulfide or methane, why they are non-polar compounds, we say because the difference is in electronegativity is relatively low. Okay, the second give reason, the polarity of water is more than ammonia. Why water is considered as a stronger polar compound than ammonia? Because when we calculated the difference in electronegativity between the water atoms and ammonia atoms, in water the difference in electronegativity was 1.4, but in ammonia it was 0.09. So the difference in electronegativity in water between water atoms was higher than the difference in electronegativity between the ammonia atoms. That's why the polarity of water is more than the polarity of ammonia. Water is considered as a stronger polar compound. Why? Because the difference in electronegativity in water is more than ammonia. The third property in the lesson is metallic and non-metallic property. We said we have three properties in this lesson, which are atomic size, electronegativity, and metallic and non-metallic property. So now we will talk about metallic and non-metallic property. We have four types of elements. We know from them metals, non-metals, and noble or inert gases. There is a new type which is called metalloids or semi-metal. So we have four types of elements. The elements may be metals or non-metals or metalloids, semi-metals, or noble gases, noble or inert gases. In groups, by increasing the atomic number from up to down in the vertical column, the atomic size increases. Why? Give reasons. Because by increasing the atomic number, we need more energy levels to distribute the electrons, those electrons. So, by increasing the atomic number from up to down in the group, we need more energy levels, so the number of energy levels also increases. So, by increasing the number of energy levels, the size of the atom will be larger. So, in the groups, by increasing the atomic number from up to down, the atomic size increases. Why? Because the number of energy levels increases, and this gives the atom more size. As we have more energy levels, the size of the atom will increase. So here we give reason: due to the increase in the number of energy levels. So the atomic size of elements of the same group is directly proportional to the atomic number. Here we have a direct relation between the atomic size and the atomic number in group. In period, it was indirect relation, but here in group, it's a direct relation between the atomic size and the atomic number. The electronic configuration of phosphate ion is similar to or same with the electronic configuration of neon, Ne10. Neon is a noble gas and it has 10 electrons. Here in this table we have three examples for metals. We have sodium, we have magnesium, we have aluminium. First, sodium. Sodium Na11, it has 11 electrons. When we make electron configuration for it, so it will be 2, 8, 1. 2 in K, 8 in L, 1 in the energy level M. So 281, it will lose this one electron and it will convert to sodium ion Na, and it will carry one positive charge because it lost just one electron, and it will be 28. 28 is just like the electronic configuration for neon. Neon has 10 electrons and its electronic configuration also is 28. What about magnesium? Magnesium Mg12, it has 12 electrons and its configuration will be 282. It will lose those two electrons and it will convert it to positive ion Mg, and it will carry two positive charges because it lost just two electrons, and the electronic configuration of the ion will be 28, also like the electronic configuration of neon, 28. What about aluminium? Al13, it has 13 electrons, so its configuration will be 2A3, Al positive 3 in the ion because it lost 3 electrons, and the configuration of the ion will be 2,8, also like the electronic configuration of neon. So the electronic configuration of positive ions is like the electronic configuration of neon, Ne10. Second type of element is nonmetals. Nonmetals have more than 4 electrons in the outermost energy level. Nonmetals are the opposite to metals. Nonmetals are opposite to the metals. They have the opposite properties. So nonmetals don't lose. Nonmetals gain electrons because they have more than 4 electrons in the outermost energy level, and the atoms want to be 8 electrons in the outermost energy level, so it's easier for them to gain, not to lose, to complete the 8 electrons. So nonmetals gain electrons, and when they gain electrons, they convert to negative ions. Negative ions. So nonmetals make negative ions, and the negative charge of the negative ions equal to the gained electrons. If the atom gain 1 electron, so it will carry 1 negative charge. If it gains 2 electrons, so it will carry 2 negative charge. If it gains 3 electrons, so it will carry 3 negative charge. So the negative charge of the negative ions equal to the gained electrons. Electronic configuration of negative ion is similar to or same with the electronic configuration of argon, Ar18, and argon also is a noble gas. For example, we have here three examples of nonmetals like phosphorus, sulfur, and chlorine. First, phosphorus, P15, it has 15 electrons, so its configuration will be 285, so it will gain 3 electrons. P negative 3, so its configuration will be 288, like what? Like argon, Ar18, 288. Okay, sulfur, S16, so its configuration will be 286, S negative 2, because it has to gain 2 electrons to make the 68, so the configuration of the negative ion will be 288, also like the argon, 288. Chlorine, Cl17, 287, so it has to gain 1 electron, so it will be 288, just like argon, Ar18, 288. So the electron configuration of the negative ions is like the electron configuration of argon. The third property in the lesson is metallic and non-metallic property. We said we have 3 properties in this lesson, which are atomic size, electronegativity, and metallic and non-metallic property. So now we will talk about metallic and non-metallic property. We have 4 types of elements. We know from them metals, non-metals, and noble or inert gases. There is a new type which is called metalloids or semi-metal. So we have 4 types of elements. The elements may be metals. Type of element is metalloids. Metalloids, we didn't study it before, but metalloids are the elements which have the properties from both metals and non-metals. They have properties from metals and from non-metals. Examples, we have boron, B5, and its electronic configuration is 2, 3, so it's like metal. And we have silicon, it's I14, 2, 8, 4, so it's like non-metals. And we have another examples like arsenic, germanium, and tellurium. graduation of metallic and non-metallic property in the modern periodic table. This table here shows the position of metals and non-metals and metalloids and inert gases in the modern periodic table. All the cells which have the yellow color are metals, and the cells with the dark yellow are metalloids. Cells with the purple color are non-metals, and the green cells are inert gases, which are located in group 18. And as we can see that each period starts with metals, which have the yellow color. So each period starts with metals, except period 1, but each period starts with strong metal. And as we go from the left side to the right side, the metallic property is decreasing, and I will tell you why in the next slide. But here, first we meet with metals in the left side, then as we go from the left side to the right side, then we meet metalloids, and after metalloids we meet what? The non-metals, and then at the end of the period, the inert gases. So each period starts with metals and end with noble gases or inert gases. Each period starts with metals and ends with noble gases. So in the same period, first we have metals, then metalloids, then non-metals, then inert gases. Now we'll talk about the graduation of metallic and non-metallic property in periods. As we said, each period starts with strong metal. Strong metal. Why? Because in the left side, the metal has the element has larger size, larger size than the element in the right side. Okay, and as the atomic size is decreasing from the left side to the right side, the atomic size is decreasing, so electrons get nearer to the nucleus, so the attraction between electrons and the nucleus increases. Because attraction increases, so it's not easy for the nucleus to lose electrons as the electrons are near to it. So again, each period starts with strong metal. Why it's strong? Because it has larger size than the metal in the end or in on the left side, on the right side. And as the size of the atom is decreasing, as we go from the left to the right, the size decreasing. So the attraction increasing, attraction between nucleus and electrons increasing. So it's not easy to lose electrons. That's why as we go from the left to the right side, the electronegativity, the metallic property, now we are talking about metallic property, is decreasing. So in number 2 here, by increasing the atomic number, and as we said, the atomic number is always increasing. So by increasing the atomic number from left to right side in the periodic table, the metallic property decreases. Why? Because attraction force increases and it's not easy to lose electrons. So metallic property decreases till we reach the metalloids. And after metalloids, we meet with the non-metallic property, non-metallic elements. And the non-metallic elements or property increases till we reach the strongest non-metal in group 17. Why the non-metallic property increases? Non-metallic is to gain. And as we said, when we go from the left to right, attraction increase. Attraction increase means that the electrons go nearer to the nucleus. So it's a gaining. So it's not losing, it's gaining, and the gaining related to the non-metallic. So the metallic property decreases in period and non-metallic is increasing till we reach the strongest non-metallic property in group 17. Then we meet with the inert gases in group 18 or zero group. So as we said, the period starts with strong metal, the metal which can lose more because it has the large size, and then the period ends with inert gases or zero group. This shows the relation between atomic number and metallic property and non-metallic property in period. Okay, by increasing the atomic number, we said that the atomic number also increasing from left side to right side. Here we have the third period, sodium, which starts with sodium. So sodium and magnesium and aluminum are the strongest metals, but as we go from left to right, the metallic property is decreasing, and then we meet with the metalloids, which is silicon here with the yellow color, so it's metalloid. After that, we meet the non-metallic element, which starts with phosphorus, and then the non-metallic property is increasing. Phosphorus, sulfur, chlorine. Chlorine considered here in the third period the strongest non-metal. Okay, then the period ends with argon, which is a noble gas. So the period starts with sodium, which is strong metal, then metallic property decreases, then we meet with silicon, which is metalloid. After that, we meet non-metals till the non-metal property is increasing. Till we meet fluorine, which is the strongest non-metal. After that, the period ends with argon, which is noble gas or inert gas. Now we will talk about the metallic and non-metallic property in groups. We have groups which are metallic groups and other groups are non-metallic groups. Examples for metallic groups, group 1A. In group 1A, as we go from up to down in the group, the atomic number is increasing and also the metallic property is increasing. Why? Because we said before that the number of energy levels is increasing as we go from up to down. And by increasing the number of energy levels, the attraction force between the outermost electrons and the nucleus is decreasing. And as the attraction is decreasing, so it's easy to lose electrons. And the metallic property is to lose. And once it's easy to lose electrons, so metallic property increases. So again, in groups, in metallic groups like group 1A, as we go from up to down, the attraction force is decreasing, so losing is easier. Losing electrons is easier because there is no attraction force or it's decreasing. So the metallic property is increasing in group 1A. Note, cesium is the most metallic element in group 1A. Why? Because it has the largest atomic size and the largest number of energy levels. Okay, lithium is the least metallic element because it's up in the group, in group 1A, and it has the least atomic size in this group and the least number of energy levels. So the attraction force for this lithium is large, so it's difficult to lose. So the metallic property is less. And cesium is down in the group and it has a larger atomic size and larger number of energy levels, so attraction is decreasing, so it's easy to lose for cesium. So the metallic property of cesium is larger than the metallic property of lithium. So cesium is the most metallic element in group 1A. Lithium is the last metallic element in group 1A. So there is direct relation between metallic property and the atomic number in group 1A, and as we said, the atomic number is increasing from up to down, so metallic property also increasing, so it's a direct relation. In non-metallic groups like group 7A, by increasing the atomic number from up to down, the non-metallic property decreases. Why? Because the atomic size is increasing, so electrons are far away from the nucleus, so the attraction force is increasing. As the attraction force is decreasing. As the attraction force decreases, so it's easy to lose, not to gain. So gaining here is difficult, so the atoms can't gain because there is no attraction force. Electrons are running away from the nucleus. So the non-metallic property decreases because attraction force decreases, so it can't gain the electrons. Okay, so that's why fluorine is the strongest non-metallic element in group 7A because it has the smallest atomic size. As it has the smallest atomic size, so the attraction force in fluorine is high. Because the attraction force is high in fluorine, because then electrons are near to the nucleus, so it's easy for the atom to attract or to gain electrons. So non-metallic property is high for it. And as we go down in this group, the atomic size is increasing, so electrons are going away from the nucleus, so the attraction is decreasing, so gaining electrons decreasing, so non-metallic property decreasing, until we reach the iodine or iodine. It's the least non-metallic element in group 7A because it has the largest atomic size in this group. That's why its attraction force is the least. So gaining electrons for it is difficult. So there is indirect relation between the non-metallic property and the atomic number in group 7A because as we said, when we go from up to down, the atomic number is increasing and the non-metallic property is decreasing. So it's indirect relation. From all what we said, we can conclude that there is a direct relation between atomic size and the metallic property. Atomic size and the metallic property, direct relation. As the atomic size decreasing, metallic property decreasing because attraction increasing, and the metallic related to attraction. And when the atomic size is increasing, metallic property increasing because the attraction decreasing. So the element can lose easily the electrons. So again, there is a direct relation between atomic size and the metallic property. Atomic size increases, metallic property increases. Atomic size decreases, metallic property decreases. And there is a direct relation between electronegativity and the non-metallic property. When the electronegativity increases, so attraction increases, so it's easy to gain, so non-metallic property is increasing, and vice versa. When the electronegativity decreasing, so attraction decreasing, so the element can gain, so the metallic property decreases. Then we have two friends and two friends. The first two friends are atomic size and metallic property. They increase together and decrease together. The second or the other two friends are electronegativity and the non-metallic property. They are increasing together and decreasing together. Conclusion. In periods, as we go from left to right side, atomic size decreases, metallic property decreases, because we said they are friends, decreases together and increasing together. And the non-metallic property is increasing because it's opposite to metallic property. But in group, as we go from up to down, atomic size increases and metallic property increases, but non-metallic property decreases. Chemical properties of metals. To know the chemical properties of metals, you should know some reactions. We should study some reactions. First, we will study the reaction of metal with dilute acids. Examples for the metals, magnesium and zinc. Okay, if we add active metal like magnesium or zinc with acid, and this acid must be diluted. Diluted means we are adding water to it. It gives us something called salt of an acid, and the hydrogen gas is evolving. Okay, for example, if we put magnesium with hydrogen chloride or hydrochloric acid and it's diluted, that's why we wrote the word del here. So magnesium will take the place of hydrogen gas and it will be magnesium chloride and the hydrogen gas will be evolving. Here in this test tube we are adding magnesium stress, the silver one down in the tube, and we are adding diluted hydrochloric acid. Then we can see the bubbles. Those bubbles are the hydrogen gas, because we said hydrogen gas will evolve and it will give us the salt of acid, which is magnesium chloride. In reaction, the reaction of metal with oxygen. If you are adding metal with oxygen and we give this reaction heat or burning, it will give us something called basic oxide. For example, if we put a magnesium with oxygen, it means that we take a magnesium strap or magnesium ribbon and we burn it. Burning means that the magnesium ribbon is reacting with oxygen on the air. Okay, so a triangle here means that we are burning the magnesium ribbon, we are giving the reaction heat, and the result will be magnesium oxide, MgO. Magnesium oxide, we call it basic oxide. If we took the basic oxide, which is magnesium oxide, and we put water in it, the result will be something called alkali. So magnesium oxide, MgO, plus water, H2O, the result will be magnesium hydroxide, and we call it alkali. Here we are adding magnesium strip, we are burning a magnesium strip in a jar filled with oxygen. So it will give us magnesium oxide. Then we add water, and the water will turn magnesium oxide to magnesium hydroxide, which we called alkali. Alkali like basic, it's a basic. So by adding litmus solution, the color of this solution will turn to blue because alkaline solutions like magnesium hydroxide turns the litmus solution into blue color. Reaction of metals with water. The reaction of metals with water depends on the chemical activity series. What is the chemical activity series? It is an arrangement of metals in descending order according to their chemical activity. They arranged the elements in descending order according to their chemical activity the as the first element in the series has is the strongest metal, so it has the highest activity in the reactions. And as we go down in this series, the chemical activity and the reactions, their ability to react decreases. So it's in descending order from the higher activity in reaction to the least activity in reaction. And we call this series chemical activity series. And as we saw that the reaction of metals with water depends on the chemical activity series, as the first two elements in this series are potassium and sodium, and they are having the highest activity, the highest chemical activity in reactions. Once we put potassium and sodium in water, they react instantly with water, and the hydrogen gas evolves and it makes a pop sound. Then we have calcium and magnesium, and they react very slowly with water, with cold water. Because as we said, as we go down in this series, the chemical activity is decreasing. Then zinc and iron, they react with hot water vapor at a high temperature only. To make zinc and iron react, we must add hot water vapor and in higher temperature, high temperature. Then we have copper and silver. They don't react with water. That's why they are down in the chemical activity series, because they have the least activity, the least chemical activity. Now we will talk about the chemical properties of nonmetal. First, the reaction of nonmetal with dilute acid. Nonmetals like carbon and sulfur don't react with dilute acids such as hydrogen chloride. We said in metals that they react with the diluted acid and give us hydrogen gas. That's for metals, but nonmetals don't react with dilute acid such as hydrogen chloride. So metals react with dilute acid and give us hydrogen gas, but nonmetals don't react. 2. The reaction of nonmetals with oxygen. If we add or burn nonmetal in air, then burning, it means that we have heat in this reaction. It will produce acidic oxide. And metals give us basic oxide. Non-metals give us acidic oxide. So metals with oxygen, basic oxide. Non-metal with oxygen, acidic oxide. Okay, non-metals like what? Like carbon, which is the cool. If we burn the coal or carbon in air, that means we are adding carbon or non-metal with oxygen, and here burning means heat. So it will give us carbon dioxide. Carbon dioxide. So if we burn the carbon or the coal, it will give us carbon dioxide, which is acidic oxide. Oxide is a non-metallic oxide, which means that we have non-metal plus oxygen, and this non-metallic oxide, when we add water to it, it dissolves in water, forming acidic solution or acid. And this acidic solution or acid turns the litmus solution into red. The alkaline solution was turning the litmus solution into blue, but here the acid or acidic solution turns the litmus solution into red. So here if we have acidic oxide like carbon dioxide and we add water to it, H2O, it gives us acid. Here carbon dioxide plus water, it gives us what? carbonic acid. And when we add water to carbonic acid, it turns into red. In figure 1, when we are burning a piece of coal or carbon, so burning carbon means that we are making a reaction between carbon and oxygen, and this produces carbon dioxide, which is acidic oxide or non-metallic oxide. In figure 2, after adding water to the acidic oxide or carbon dioxide, it produces acidic solution or acid, which is here carbonic acid. And it turns the litmus solution into red. So acidic solution or acid turns the litmus solution into red. This picture here shows that when we are adding litmus solution into acidic solution, the color is turning into red. Here we have the color of the acidic solution and alkaline solution after adding litmus solution. Litmus solution is turning with acidic solution into red, and it's turning with alkaline solution into blue. Some metal oxides, which we call amorphic oxides like aluminium oxide. Why? Because they can react with acid as a base and also can react with base as an acid. So they can do both. Can be an acid if they are reacting with a base, and they can be a base if they are reacting with an acid. And it gives us salt and water. Okay, how can we differentiate between calcium oxide and sulfur trioxide? Calcium is a metal, sulfur is non-metal. So we use litmus paper, and by using litmus paper with calcium oxide, it will be turning into blue. It will turn into blue. It means that calcium oxide is a base. And if we use the litmus paper with sulfur trioxide, it will turn into red, which means that sulfur trioxide is acid.